Good morning, everyone. Myself, Dr. A P Srivastava, Department of Physics, DBS College, Kanpur. Today, we are going to discuss rectifiers and transformers and their respective applications. Rectifier. A rectifier is an electrical device that converts alternating current to direct current. Its reverse operation is performed by inverter. Rectification is the process in which conversion of AC is converted into DC. This involves a device that only allows one-way flow of current. There are two types of rectifier: half-wave rectifier, full-wave rectifier. Half-wave rectifier. In half-wave rectifier, one half of each AC input cycle is rectified. When the PN junction is forward biased, it gives little resistance, and when it is reverse biased, it provides high resistance. This is the circuit diagram of half-wave rectifier working. When AC supply is switched on, the AC voltage appears across the terminal AB at the secondary windings. During positive half cycle, terminal A is positive with respect to V, and diode is forward biased. Therefore, it conducts current, and current flows through load resistor RL. During the negative half cycle, when the diode is reverse biased, it does not conduct any current. Before, no current flows through RL. Full wave rectifier. In full wave rectifier, when AC supply is applied at the input, during both the half cycle, current flows through the load in the same direction. In it, two diode is used for rectification. Classification of full wave rectifier. Full wave rectifier is of two types: center tapped full wave rectifier, full wave bridge rectifier. Center tapped full wave rectifier. The center tapped full wave rectifier implies a transformer with secondary winding AB tapped at the center point C. It converts AC into DC, AC input to DC input. This is circuit diagram of full wave rectifier. When AC is switched on, the alternating voltage Vin appears across terminals AB of the secondary windings of the transformer. During the positive half cycle, end A becomes positive and end B becomes negative. Thus, device D1 becomes forward biased and D2 becomes reverse biased. When diode D1 is conducting current, current flows through D1, and when load resistance and upper half of secondary windings. During negative half cycle, end B becomes a positive with respect to making diode. Making diode D2 forward biased and diode D1 reverse biased. Now the current will flow through diode D2, load resistance in lower half of a secondary winding. This is waveform of rectifier. In full wave rectifier, an ordinary transformer is used in place of center tap transformer. The circuit forms a bridge connecting four diodes in full wave bridge rectifier. This is circuit diagram of bridge rectifier. When AC supply is switched on, the alternating voltage Vin appears across the terminals AB of secondary windings of the transformer. During positive half cycle, end A become positive and end B become negative. The diode D1 and D2 are forward biased and diode D3 and D4 are reverse biased. During negative half cycle, end A becomes negative and end B positive. The diode D3 and D4 are forward biased and diode D1 and D2 are reverse biased. Therefore, current will flow from D3, D4, RL and secondary winding of transformer. Rectifiers are widely used for power supplies, battery chargers, motor drivers, and signal demodulation. They enable electronic devices to operate efficiently from standard AC mains. Some important applications of rectifier includes power supply units, crucial in TVs, laptops, and mobiles to convert mains AC to usable DC. Battery charging systems used in chargers for phones, cars, and other portable devices to convert AC to stable DC. Motor drivers used in variable frequency drivers and DC motor drives to convert AC input to controllable DC. Audio amplifiers. It supplies stable DC voltage to drive audio components. Signal modulation used in AM radio receivers to detect signals. Electric welding. It converts AC input into a DC current for welding applications. Rectifiers are major components in power supplies, particularly in switching power supplies used across numerous electronic devices. These rectifiers efficiently convert alternating current from mains power sources into direct voltages, which are essential for powering both digital and analog circuits. In devices ranging from smartphones to computers, televisions, rectifiers ensure a stable and reliable power supply, enabling seamless operation. Rectifiers may be used in AC DC converters and receivers, which are applied in different industries such as automotive and industrial, as well as consumer electronics, to convert mains grid AC power into DC power that is used for charging batteries. In various industries, including automotive, industrial, and consumer electronics, rectifiers are indispensable for battery charging applications. They facilitate the conversion of mains grid AC power into DC power used for charging batteries. This ensures that batteries in vehicles, portable electronic devices, and industrial equipment receives the necessary power for optimal performance and longevity. Rectifiers make battery charging efficient and reliable. Rectifiers are used in electroplating. Rectification is utilized in electroplating environments by alternating current to direct current conversion for metal deposition processes, so that metallic ions can be placed onto conductive surfaces for coating and finishing purposes. By providing a steady DC current, rectifiers enable the controlled deposition of metallic ions onto conductive surfaces during electroplating. This ensures uniform and high quality coating and finishing, which is essential for various industries such as automotive, aerospace, and electronics manufacturing. Rectifiers are used in the process of electrolysis. A rectifier is essential for electrolysis processes as it provides current density to push the reactions forward, for example, toward splitting water into hydrogen and oxygen or metal extraction. For example, in water electrolysis, rectifiers help split water molecule into hydrogen and oxygen gases, which can be used for various industrial applications including hydrogen, fuel production. Additionally, rectifiers aid in the extraction of metals from their ores through processes like electrolytic refining. A rectifier is an instrument used in welding machines for an AC to DC conversion of the power, which stabilizes the electrical connection. It is adjustable and suitable for arc welding and other welding methods. The conversion from alternating current power to direct current power stabilizes the electrical connection. This makes it suitable for various welding methods such as arc welding. Rectifiers in welding equipment ensure consistent and adjustable power delivery. This allows welders to control the intensity and duration of the welding process. Limitations of rectifier. First one is voltage ripple. A rectifier provides a pulsating output whose DC component may give rise to ripple in the output waveform. This ripple can cause fluctuations in the output voltage or current, which may not be suitable for sensitive electronic devices or systems. Power factor degradation. Losses in a power system can be related to the inductive character of rectifiers. Such a power factor can be considered responsible for increased utilization and reduced efficiency of the overall system. Voltage regulation. Rectifiers have limited or low voltage regulation capability. The output voltage is determined by the input voltage, load impedance, etc. This lack of regulation may be sufficient, may be insufficient for applications requiring precise control over the output voltage. Heat dissipation. Rectifiers create a huge amount of heat through the process of operation, especially at high currents or when operating near their maximum ratings. The main advantage of rectifiers is its simple circuit and low cost. But, but its disadvantages are the output current in the load contains, in addition to AC component of basic frequency equal to that of the input voltage frequency. Ripple factor is high and an elaborate filtering is therefore required to give steady DC output. DC saturation of transformer core resulting in magnetizing current and hysteresis losses and generation of harmonics. These are the main disadvantages. Transformer. A transformer is a static device. The word transformer comes from the word transform. Transformer is not an energy conversion device, but it is a device that changes AC electrical power at one voltage level into AC electrical power at another voltage level through the action of magnetic field, but with a proportional increase or decrease in the current ratings without a change in frequency. It can be either to step up or step down. Types of transformer. Transformers is of many types. Instrument transformer, step up and step down transformer, single phase and three phase transformer, power transformer, distribution transformer. Instrument transformer is of two types: current transformer, potential transformer. Working of the transformer. The main principle of operation of a transformer is mutual inductance between two circuits which is linked by a common magnetic flux. A basic transformer consists of two coils that are electrically separate and inductive, but are magnetically linked through a path of reluctance. According to the Faraday's law of electromagnetic induction, the induced EMF due to varying flux is given by E is equal to N d phi upon dt. Vp is equal to Np d phi upon dt. Taking the ratio of the two equations, we get Vp upon Vs is equal to Np upon Ns. For an ideal transformer, Pn is equal to Pout. Transformer efficiency is given by output power upon input power into 100. Another formula is efficiency is equal to P output upon P out plus P losses into 100. Ideal versus practical transformers. A transformer is said to be ideal if satisfies the following properties. It has no losses. Winding resistance has 0. There is no flux leakage. Efficiency is 100%. But in practical, there are some losses in transformer. Now losses in transformer. Copper losses, core or iron losses, hysteresis losses, and eddy current losses. Application of transformer. Transformers are utilized across nearly every sector of modern life, from the massive scale of national power grids to the tiny components inside your pocket. The fact that an AC voltage can be stepped up or stepped down has application in transmission of power from the electricity generation plants to the users. Generally, these plants are quite far away from the actual areas where the power is used. Power is transmitted through several hundred kilometers of wires before it is used. Because of the resistance of these wires, some energy is lost in joule heating in the form of I square RT. The plant can supply a fixed power depending on its capacity. If this power is supplied at a high voltage, the current is small. Correspondingly, the loss of power in transmission is small. So the voltage at the electricity generation plant is stepped up to say 66 kV and fed to the transmission lines. In a town or city, the voltage is stepped down to the required value such as 220 volt. Power distribution and transmission. This is the most critical application of transformers. Step up for long distance. Power plants generate electricity at relatively low voltages. Step up transformers increase this voltage to hundreds of kilowatts for transmission. This minimizes energy loss caused by resistance in long distance wires. Step up for consumption. Before electricity enters your neighborhood, step down transformers at substations and on utility poles reduce the voltage to safe usable levels, typically 110 volt, 230 volt, or even 250 volt. Consumer electronics and charging. Almost every device that plugs into a wall outlet requires a transformer to function. Voltage adaptation. Most electronics operate on low DC voltage, 5 volt to 20 volt. Small transformers inside your laptop charger or phone block step down the 120 volt or 230 volt wall power to a level the device can handle. Isolation. These transformers also provide galvanic isolation, ensuring that if a fault occurs on the grid, the high voltage does not reach the user or the delicate internal circuit of the device. Third one is industrial and heavy machinery application. Heavy industry uses specialized transformers to manage massive energy demands like electric furnaces used in steel manufacturing. These furnaces require incredibly high currents at low voltages. Welding transformers. These provide high current to create the heat necessary for melting metal while keeping the secondary voltage low for operator safety. Third one, variable speed drives. Transformers help manage the power supplied to large industrial motors in factories and pumping stations. Fourth one is signal and audio processing. Transformers are not just for high power, they are essential for data and sound. For example, audio matching. In high-end audio systems, transformers match the impedance between a microphone and an amplifier to ensure the highest sound quality and prevent distortion. Second, impedance matching in communication. This is used in telecommunications to match the characteristic of transmission lines, ensuring signals travel clearly without reflecting back. Fifth one is measurement and safety. Instrument transformers. In high voltage environments, it is too dangerous to connect a standard voltmeter or ammeter directly to the line. Current transformers and potential transformers scale the power down to tiny safety levels so that meters can accurately monitor the grid's health. Second one is rectifiers. Transformers are used in conjunction with rectifiers to convert AC power from the grid into DC power, which is necessary for battery charging systems and electroplating. Before concluding, this is very important to tell you that transformers are used in solar and wind systems to manage voltage levels. Transformers are essential in modern electrical systems and enable efficient energy use. Thank you.